A little bit of death by text here, but the main thing to highlight is there was a lot of different diverse interests in ICESat-2 bathymetry and a lot of different questions that our group sought to answer. Just kind of going through order, there's a very obviously a changing Arctic environment and bathymetry. There's a lot of new avenues opening up for bathymetry and how ICESat-2 can be useful for studying bathymetry in the Arctic and other hard to reach areas. So from a hydrographic standpoint, there's a lot of interest. There's also a lot of interest from an ecological standpoint, studying environments like mangroves and areas like coral reefs and studying the health of seagrass. And then there's also a significant data science component of extracting bathymetric and surface signals from ICESat-2 data. There were a broad set of focus areas. Part of this is stemming from the fact that there's not actually a derived bathymetric product yet. So a lot of the group, instead of where you can maybe get started pretty quickly with something like land ice, understanding how the bathymetric data is somewhat hidden inside the raw ATL03 files. The components of ATL03 that you need to, reliably access bathymetry, the best methods of signal classification. The signal classification algorithms have not quite yet been tailored to bathymetry, so exploring things like that. And then as well as just developing tools for bathymetric analyses and workflows, using some of the great tools that we've seen in tutorials so far this week. So these are just some of the areas that our members kind of self-selected into. This is not everyone that identified as part of the bathymetric working group, but there's been a lot of cross-collaboration between these segments as well, and additions from folks all throughout the Hack Week that have been really, really great. So just a couple quick wins from this week. I think we did a pretty significant amount of exploration of bathymetry data in a variety of diverse environments, getting a sense of different signal classification, pros and cons, and getting a sense of ICESat-2 bathymetric performance in a variety of areas. As anyone who's worked with ATL03 knows, it can blow up in terms of memory pretty quick. And I think Sliderule in particular has opened up a lot of great avenues for bathymetric analysis using ATL03 without causing too many issues in terms of local memory, and that's been really great. We've also explored a lot of different visualization methods for visualizing the bathymetry within ATL03 files, and developed some Python tools and some skill sets for future work developing Python tools in collaborative environments like this Hack Week. Some of the issues that I might have already touched on is some issues that we had across the group between Git, Python, and Jupyter. There was just a very diverse set of skills and backgrounds and familiarity with some of these tools. So making sure that everyone was on the same page for that was a key component this week. Another big one was getting to know the ATL03 data. There's a lot of different parameters. Some of them are more useful for bathymetry than not. And then programming skills, the object-oriented programming tutorial was very useful as well for our group, but improving how we modularize our tools going forward, I think, is a big goal. This is a quick slide we had for anyone who's interested in looking at bathymetry data going forward and some of the data access considerations we ran into. Bathymetry, depending on your bounding box, might be too big and you may end up experiencing some timeout requests. However, there may also not be too much signal if you're looking at a relatively small bay or a small inlet area. So to be very mindful of your bounding boxes. And despite some of the benefits that Sliderule has for subsetting ATL03 data, the water surface is a significantly dense photon return section, and it can really blow up your memory if you're not careful. And then some quick feedback we got this morning from members in the group is that IcePix and Sliderule were both very useful for different reasons in our experience. Sliderule is especially useful for subsetting, and IcePix was also helpful for extracting other ATL03 parameters that are useful for bathymetry analysis and calculations such as refraction correction, which we'll talk a little bit about later. And I think this is the last slide before I'll hand it off to Eli, but these are just a couple of the different locations that we looked at this week, from glacial lakes to Hawaii and the Alaskan coast. I think a diverse set of environments, to be sure. Eli, do you want to take it from here?
Yep. So the first step, and really our first 2 days, was just getting to know the ICESat-2 data and to look at a few different regions. So, and we started that using open altimetry, by modifying one of the tutorials that we were given. And this is an example from that tutorial, actually. And this is from the Bahamas. And if you look at this, you can see clearly the ocean surface and then the bathymetry. This is an example where the bottom bathymetry is really obvious. But we wanted to look at a few different places to get a sense of, you know, what does it look like in general? It definitely doesn't look like this in general. Okay, next slide. So we also used Sliderule in this data exploration part. And this was really nice because it was easy to create these kinds of visualizations. So we could set up a bounding box and then visualize how much data we had there, because we found, as Jonathan mentioned, that there was a lot of variability in how much data we had. Another nice thing with that is it was quite easy with the output, which is a GeoPandas data frame, to create these nifty 3D plots, and you're going to see more of these. And that really helped us visualize whether in that location we would be able to get a bottom bathymetry signal. Next slide. So this is another way that we're playing with Sliderule. Actually, Jonathan, can you go back up to that open altimetry? Let me just show everyone that. One more. No, back up. Yeah, that one. Okay, so a key question for us was, okay, what about the existing products? Can we use some of those to get at the bottom bathymetry? And that was, you know, easy to use open altimetry to do that because it returned the products that are listed in the bottom there. So you can plot all those. So if you want to do that, that's nice. Okay, now back to the comparison of the ATL. Yeah, right there. So this is an example comparing the ATL08 classifications and the yet another proton classifier that you can play around with Sliderule. And Jonathan's going to show a nice example of using that in the Bahamas, where it actually does a really good job. In this case, this is, what am I looking for? I forget where this is, but this is, I think this is actually Hawaii. This is Hawaii, and you can see the water gets deep pretty quickly beyond the limits of the photons. So it's not such a clear example. Okay, next slide. Go ahead, let's go to the examples. Yeah, okay, so now we're going to go through a series of our examples in very different parts of the world. Jonathan's going to lead off.
So just really quickly, here is a great demo of how useful Sliderule can be for compiling a whole bunch of ATL03 tracks with bathymetry in a way that has been very problematic for me in the past, actually, and it's been really useful. But people tend to get used to looking at bathymetry in these single profiles, and Sliderule has been really useful for compiling these all together. And in the Bahamas, where you have a really strong seabed, you actually get a very nice almost profile of the overall bathymetry when you have a high density of ICESat-2 tracks here. And I really can't exaggerate how much easier Sliderule made this than going through this and individually downloading all these ATL03 files and filtering them out yourself. That's all I have to say about this one. I guess really quick, and we also found that YAPC tended to do a lot better than ATL08 as far as signal classification, which is really great to see, and it's exciting that it's already been integrated very nicely. Eli, do you want to take this back over?
So the Bahamas example is an example where the bottom bathymetry, you can see it, the water is fairly clear, so the photons go through it. A lot of people in our group were interested in Alaska, and particularly the Alaska coast. This is an example of a different data set. And here we go, this sort of in the bottom bottom right is the photon plot. And starting at about latitude 70 or so, that's where the ocean starts. And you can see that we really don't have a bottom bathymetry signal here. It's either dropping off too quickly or the water's just too turbid, something like that. And then let's see, I think Bruno, were you going to talk about this? Great.
Yeah, just like on the same line as the North Alaskan coast here, I was trying to understand like how good these data could be, like could perform on turbid environments, or where you have general a high density of or a high concentration of suspended sediments. So I tried to use the code that Eli had modified to to find profiles along proglacial lakes and river delta in Alaska. And again, it looks like to a certain extent you can use the photon responses like to kind of understand how turbid the environment is, just like in the YAPC score here. So the higher, like the blue colors are high confidence. And in this case, it looks like there are high confidence photons coming from several meters beneath the surface of the water. But again, it's hard to tell if that's if we actually do have a surface down there, or if it's just like because that's where the photons are just stop. And if you go to the next slide, we see that here in this case we have a profile that passes through a little island, and we see in the middle that indeed it just stops abruptly. Meaning that probably what we see is just like the limit of penetration of the photons instead of anything that is close to the bottom of the lake. Next slide. Same thing, but for a river delta. It would be interesting if we were to have more time series of ICESat data for river deltas environments to see maybe interannually how the sediments move. But in this case, again, we really have a very, very thin layer of photons, and that's all we get. So it does not penetrate in turbid environments. And I think that's all I have to say.
We briefly explored gridding and rasterizing ICESat-2 bathymetric data, but I think one of the key issues we ran into in terms of how to make ICESat-2 data, bathymetry data specifically into a nice raster format is that there's not already a derived product, and there's a great need for a reliable form of bathymetric feature extraction and signal extraction. And I know that along those lines, we had a couple group members looking at that as well. So Kim and Yuri, I believe these, would you all like to speak to these as well?
Yes, please. Can you hear me?
Yes.
Okay, so we tried to combine Sentinel-2 data with ICESat-2 data, and obviously it's ATL03 because we need to go down to photon events. So it seems attractive to find the pseudo bathymetry from Sentinel data and fit in some way optimally to the noisy cloud of underwater measurements from ICESat data. And and then just to find the parameters which are usually found from comparing with in situ measurements. So 3 for Lysenga's model, 2 for Stumpf data model, and for nonlinear data, nonlinear models, other parameters. So on the left, the image of pseudo bathymetry of Key West, and it has lots of gaps, and these gaps came from all sort of problems. Some white is obviously land, and there shouldn't be any bathymetry, but also there are lots of pixels, because it's a raster imagery, where the pseudobathymetry does not have meaning. So we need some means to smooth this bathymetry somehow. So on the right is attempt to smooth, and it hasn't been very successful yet. Next slide, please. So we tried to find out if the confidence values have any meaning for bathymetric data. And unfortunately, we came to a conclusion that it does not. So we tried to a number of about like 30 various transects, which have clearly some bathymetric data. You will see it on the next slide. But here, I just want to say that we manually marked the photon events that we think as experts belong to bathymetric measurements, and compared to confidence values for land, ocean, and inland water. And there was no correlation whatsoever. These photon events could have 000 or 444, so confidence does not seem to matter here. Next slide, please. And here is the result of the one of the transects across the St. Thomas Island, and on the right is the is the right part of the whole transect. So the human eye clearly says this is bathy data, but there are no algorithms so far published that would be able to extract this bathymetric data. So we think that it might be useful to use shapefiles for known land, find the coastal points where the land meets the water, and just start tracking, tracing bathymetric photon events from there. But this is just an idea.
And I will speak to that, and I heard the bell, so I'll do it quickly. This is very, very unsexy work, but very necessary. The photons that are in ATL-03 have not been corrected for refraction, which means their XY location and their Z location are not correct. So something that we all need is a refraction correction, and it's something that I've needed in my own work. Now, not only is this programming, and Jonathan and Yuri both provided me with functions, Python functions that can do this, but within the data dictionaries, there's all kinds of stuff that you think, well, is that what I need? For example, for the refraction correction, you need to know the depth. Well, ATL-13 has water depth, but there's no documentation on where that has come from. And then the overall wrapper of this is saying, well, okay, we have a refraction correction, but where do we apply it? We certainly don't apply it on land. How do we find land? So that's what was done on refraction index. Progress was made, but a lot of it is just beating up on the data dictionaries of the different products. Okay. Next. All right, and then that led us to what happens next year. And sort of the holy grail, I think, for all of us is to say, can we get bathymetry extracted automatically? What you're seeing at the top is an algorithm that's based on median analysis that was implemented, that was described by a Danish researcher named Heidi Ranndal. And on the left, you see a place that it performs well. And let's face it, we all look at it and say, well, let's take a typical example, which always means the best possible example that we can find and show how it works. So you can see we did, in fact, extract bathymetry reasonably well with the data on the left. But on the right, I think a human being would in general say, well, I think I kind of see something there. Well, the median algorithm doesn't perform well. So next year, if this goes on again and we're back, may be able to advance this. The other thing, and I talked with Jonathan about this, is within the ATL03 product, you get phantom surfaces. And so you have the ocean surface, you have then potentially real bathymetry, but then you get these weird little shadow phantoms in there. That's something that we would like to be able to look at and say, let's get rid of that so we have a better chance of identifying the bathymetry.
I think that's all that we've got for this week. There's some elements here for future work, but I think I speak for everyone on the team. And I just want to say thank you all for a great hack week and a great opportunity to collaborate with some wonderfully smart people. I think we've all enjoyed it very much.